Okay, so you've probably thought about it, right? What if you could just jump to a distant galaxy in the blink of an eye? It's a classic sci-fi dream for sure. But, and this is the cool part, it's also a serious, kind of mind-bending idea that comes straight from theoretical physics. So today, we're going to dive deep into one of the universe's biggest what-ifs, the science of wormholes.
Yeah, you've seen them. From Stargate to Star Trek, these shimmering tunnels that just, poof, connect two totally different points in the cosmos. I mean, it's the ultimate cosmic shortcut, right? But here's the real question. Is this whole idea just some Hollywood magic, or is there actually some real science behind it? Well, let's find out.
So to really get a handle on wormholes, I think we have to start where most of us probably first saw them. Yeah, we're talking about the ultimate cosmic plot device, the sci-fi shortcut. I mean, think about it. If you're writing these epic stories that span entire galaxies, you've got a problem. How do you get your heroes from point A to a very, very distant point B in, a reasonable amount of time? The wormhole. Well, it became the perfect solution. It's the plot device that makes these absolutely incredible journeys possible. But that really gets you wondering, where did this incredible idea even come from? Is it all just fantasy, or is there some real science to it? Well, here's the kicker. Turns out, the idea of a tunnel through spacetime, it didn't start on a movie set. Nope. It started in the notebooks of some of the absolute greatest minds of the 20th century.
All right, so let's peel back all that fiction and take a look at the real science. This is where we get to the idea of a bridge through space-time. So what is a wormhole really? According to the actual physicists who first dreamed it up.
Okay, so at its very core, that's the definition. It's this theoretical structure that connects two completely separate points in spacetime. So try to think of it less like you're traveling through space and more like you're stepping outside of it for a minute just to get somewhere else way, way faster. The classic way to picture this is actually super simple, but it's really powerful. Okay, imagine our universe is just a flat sheet of paper. Now, to get from point A to point B, you'd have to crawl all the way across the surface, right? But what if you could just fold that piece of paper, bring those 2 points right next to each other, and then just poke a hole straight through? That's the wormhole. It's a direct path that completely bypasses that long, long journey. So you see, it's not some kind of magical portal that just appears and disappears. It's way better to think of it just like this quote says. It's a tunnel with two ends. It's a bridge that connects two different places, and maybe, just maybe, two different moments in time.
And you know that term wormhole we all use? That was actually coined by the brilliant theoretical physicist John Wheeler. But the scientific idea itself, well, that goes back even further. It comes from a concept called the Einstein-Rosen bridge, named after, you guessed it, Albert Einstein and his colleague Nathan Rosen. They were the ones who first put the idea out there.
Okay, so we've moved from the basic concept to the actual blueprint. This is what we're calling the physicist's blueprint. This is where this beautiful, wild idea gets described in the one language the universe truly understands, math. Whoa, okay, I know what you're thinking. Don't worry, you don't have to solve this. But to even create a blueprint for a wormhole you could actually travel through, physicists like Michael Morris and Kip Thorne came up with what's called a metric. You can just think of it like a set of mathematical rules, a recipe, that describes the exact shape, the geometry of this space-time shortcut. It tells you exactly how it curves and how it connects from one end to the other. And this is what all that crazy-looking math looks like when you turn it into a picture. Those rules, that recipe, lets scientists map out what they call geodesics, and that's just a fancy word for the straightest, most efficient path something could take through this weird, curved space-time. It's literally a roadmap from one mouth of the wormhole down through the throat and right out the other side. Okay, so we've got the sci-fi dream, and we've got the physicist's blueprint, which brings us to the final, and let's be honest, the most important section, real or just theory. This is the big one. It's a totally logical question, right? I mean, if you can describe something with math that fits inside the laws of physics, it should be possible. But yeah, in our actual universe, it's just not quite that simple. And here's the thing you have to remember. There's a huge difference between theory and observation. Right now, wormholes are still just a concept being studied in theoretical physics. The math works beautifully on paper, but they are purely hypothetical. As of today, we have absolutely zero observational evidence that they actually exist out there in nature. They're an elegant solution to an equation, but one we've never, ever seen in the wild. And trust me, there are some enormous hurdles to them even existing. Let's break them down. First, as we said, they're just theoretical. We've never seen one. Second, most scientists believe they would be crazy unstable. And finally, to keep one open, you'd need something straight out of science fiction, this theoretical stuff called exotic matter.
And really, that instability part, that's the key takeaway for a lot of physicists. It's kind of the fatal flaw. The thinking is that the incredible force of gravity would just cause it to collapse in on itself almost instantly.
Right, so without this exotic matter to basically prop the tunnel open, a wormhole would probably disappear almost as soon as it formed. And this stuff would need to have really bizarre properties like negative mass or negative energy, something that would literally push space-time outward and keep the tunnel from just pinching shut. The problem, we've never ever seen anything with properties like that. So for now, it's purely theoretical. So if we can imagine a shortcut like this, will we ever actually build one? I mean, that's the big question, isn't it? Right now, wormholes exist as this thrilling possibility in our stories and as a really elegant idea in our equations. They really represent the absolute boundary of what we know. But you gotta wonder, just because we can imagine it, does that mean we're destined to one day discover it? Well, I guess only time and space will tell.